Okay. Um, Welcome back. From a college competition, we have three n by n matrices which are idempotent and satisfy uh, b cubed equals abc plus 2. And you want to show a to the 6 is 1. Um, Apparently. Uh, okay. So that is a thing that can happen. Um, so I guess like the first thing is that oh crap. Green screens are struggles. The matrices doesn't actually matter, right? Because if it's true for it should be Manip. IMC is the international math competition. I think it's like a college competition. I forget exactly. I've never done it, so I don't know that much more about it. But it should be Manip because if it's true for n by n matrices, then they should be true for any abelian group satisfying the same identities. And if you write it that way, it's like, you know, there's no reason you would want to work with matrices in particular. So, like, yeah. Yeah, so it should be like some sort of alg thing, but then what? Well, okay, a to the 6 is equal to b to the 6, right? So, a to the 6. See, I'm not even going to pretend they're matrices. Let's, like, work. Oh, okay, we'll just use capital letters. That's fine. A to the 6 equals to b to the 6, which is, like, equal to abc plus 2 squared. Sorry, I lied a bit about the group thing. I meant to say algebra. It's like the algebra of... Wait, okay, actually now I'm confused. Is that thing I said about the group true? Is it like... So I feel like the multiplication can be whatever it wants, maybe? But this has two operations, so... Sorry, I might have lied about the thing about being augmented. I might actually need the linear algebra. But also like ABC plus 2. What is the ABC plus 2? So, like, group is a little bit of a misnomer because there's like both a multiplication and an addition. So it's like you're working in some generic algebra, I think. So like some C algebra. Yeah, I still don't really like the eigen thing because I feel like if n is large enough, you can make the multiplication table. Like, if it's true for it'll be true for C adjoint G for any group G if it's true for the matrices. I guess is what I'm trying to say. And so that makes me feel like I don't really want to touch the eigen things because I can't promise that ABC are diagonalizable at the same time. But on the other hand, like, I don't know. It's weird because ABC don't do anything besides exist. A to the 6. Like, I don't know. Like, I can write dumb stuff like AB cubed C. Cayley's theorem is, yeah. B to the 5th plus 2AC. So like b to the 5c is like yeah, I wonder if the strategy is to just try to get it to be a polynomial in B. A, B to the 5th C. B to the 5th is 2. Sorry, that's a mistake, I think. I left out the B, 5C. So if I think B is wow, this is weird. A squared B cubed C squared. Did I mess up? A squared. Yeah, sorry, you're right. It should be A squared B C squared, which is then which is B to the 5. So if I like fix a matrix B, actually, here's a question: is it obvious that B is even invertible? Because if B is actually invertible is not super. I might actually pull out an alg at some point. Wait, AC equals 0? No way, right? Oh, wait. A squared out plus 2AC. Why is A cubed B cubed C equal to A squared B C squared? Okay, cool. I can set square as middle part by doing stuff like ABC cubed. Yeah, that's what I'm doing with the AB cubed C. But I might actually just do linear algebra. 'Cause, like, if you know, the whole point of doing the linear algebra stuff is now you get you turn like matrices into complex numbers. Specifically, like if you fix an eigenvector, you get like it's an eigenvector of c squared. I don't know what to do with the. Where does b to the 5 equals a b to the 5th? B to the 5 is like b cubed times. Where does that come from? How did I get that? Alright, that's a good question. Where did I get that from? Yeah, that probably should be like b to the 7, sorry. I think I was like trying to multiply by like a squared c squared, which is kind of dumb, honestly. I should just. Shows being. Yeah, b to the 7 equals b would suffice if b was invertible. A plus c squared is 0. Oh, that's good. Okay, wait, so what happened? B to the 5 is ABC. I don't understand how this math works. Okay, so the claim is that So b to the fifth is equal to abc b squared plus 2b squared. You move the b squared into c's and then c's into b's. So it's like a b to the cubed c plus 2c squared. Sorry. Wait, isn't it b squared? It's like plus 2b squared, right? And then what do I combine that with? I guess, yeah, okay. The point is that okay. So b squared equals c squared. Yeah, fine. Ab cubed c plus 2c squared, which is equal to ab cubed plus 2c times c. Oh, wait. Okay, wait. Yeah, I feel like at this point I'm just wandering in a desert. Plus 2ac plus 2c squared. Okay. Okay, so we actually used the ab cubed c thing. This is like left to right. And then we also do the b to the fifth. So one of them is multiplied by a on the left and c on the right. The other is just multiplied by the square on the thing. ab cubed c. Okay, let me make this self-contained. Okay, so it's like ab cubed c is a abc plus okay, yeah, okay, Manip. Yeah, ergo ac plus c squared is 0. Repeat the argument. Also, similarly, a squared plus ac equal... well, actually, if ac plus c squared equals 0, i.e. c squared equals minus ac, then suddenly, like, the multiplication on left and right that we've been doing... Oh, let me just write it out. Similarly, a squared plus ac... Okay, so we now have, by repeating similar arguments, a squared equals b squared equals c squared is specifically equal to minus ac. And if we have that, then suddenly a lot of doors open. So like b cubed was like b cubed is equal to like minus acb Okay, so yeah, so what was I saying? So like AC times B, like minus ACB is equal to ABC plus 2ID now. And similarly, like b cubed is equal to ba squared minus bac. So we can like deal with a lot of cross terms now, like. Feel like it's important. No, I feel like it should. I don't know. I feel like it might end up just being alg-manip only. I'm not totally sure about this, but I feel like because if it's true for matrices, it'll be true for K adjoint G for any group G or something. I'm not sure. Anyways, A is invertible now, because yeah, A is invertible because now we have like A times BC plus CB is minus 2. How did you get the line with b to the 7? I mean, we're not using it, but it's to multiply by a squared on the left and c squared on the right. Maybe we should use it now that we have. Oh god. Is 2 a primitive root for infinitely many primes? Open. Oh wait, yeah, actually hang on. If A is invertible, then actually a squared plus okay, yeah, here invertible, okay? In particular A is invertible. Consequently consequently a plus c is equal to 0. Okay, wow, this is so weird. So now there's only 2 variables. So we could just do it in terms of a and b. So now we have a squared equals b squared, and b cubed equals minus aba plus 2 id. Okay, so now I can square both sides, right? Why are there only 32? 32 is pretty normal, actually, I think. But, like, I don't know. Math streams are very niche. Audience. Minus ABA. ABA. Okay, so it's like AB to the 4A. Minus 4 ABA, which is like minus 4 or something. Okay, and ABA to the 4 is actually equal to B to the 6, right? So despite the fact I was trying to get b to the 6, the b to the 6 actually cancels and gives b cubed equals 1, which means I definitely made a sign error somewhere. Because... Okay, well, what did I flip? Minus... Yeah, this is plus. And hence b cubed equals minus id. Can I just not have the id at this point? I'm just gonna leave off the id when I write this up. So b to the 6. Why does a b to the 4a? Because a b to the 4a is equal to a squared, a. Which is equal to a to the 6. Which is equal to b to the 6. Yeah. Yeah, so that happened. I still have no idea what's going on. Like, I feel like I just manipulated some things and it worked. But here we are. Yeah, it has that feeling. Thank you, Blades of Grass. This holds over all matrices. I mean, what do you expect? Like, complex is not used, which is completely understandable. Okay, maybe not F2. Yeah, okay. I agree it might not work over F2, because F2 sucks. Yeah, we did it. Okay. Thank you, team, for helping me with algebra, because I do not like manipulating expressions. Okay, we start with the following claim. Yeah, it's interesting because, like, even for high school Olympiad kids, Olympiad students don't typically work with non-commutative rings, so I don't think it's like not only is it algmanip, but it's the kind of algmanip you're not used to if you're still in high school. Yeah, okay. Yeah, I reconfigured my whole editor like yesterday, if for anyone that was watching. So a bunch of shit isn't working now as usual. Uh, yeah, but here we are. Wait, what? Okay, so I need to deal with that later. We start with the following claim. Actually, let me do it this way. So we ended up not using any of this crap, and we just started with this calculation. Yeah, Como is tough. So following the analogous argument, we now have, actually, yeah. Finishes the claim. And then claim, so then, now notice that, ABC plus 2, now since b cubed equals, how did I get BAC? Sorry, I wrote minus AB when I meant minus AC. Now we have, okay, so notice that this means that minus 2, I'm gonna leave off the IDs because I actually think they are distracting. It's 2 AB plus BAC, so C is invertible. Combined with the claim that AC plus C squared equals 0. So actually, I want to, I'm going to squeeze both of these in. Okay, so blah blah blah, and then I know you type at like 300, but I should use ulti snips. Yeah, I may do that at some point. On some recommendation, but I haven't done that yet. Okay, is that it? Okay, sure. Fine. IMC is... Where is it? Yeah, this is... I don't know. Non-Commutative algebra. What a concept. Oh, what the hell is this? AB cubed equals B cubed. Oh, really? Alright, yeah. That's pretty good. It's like AB cubed C and then B cubed. Oh. Did we miss that? Do we have an AB cubed? I don't think I ever did just one side. Okay. Oh, that's pretty good actually. Ah, lame. Okay, yeah, what was next on the list for today?